So we are going to discuss the Ampere's law. So what does this law states? So this is just another way to find magnetic field due to various structures. Now the Ampere's law defines or states basically that the line integral of a magnetic field intensity along a closed path is equal to the current distribution passing through that loop. So like we'll understand this statement in a better way, that if this is magnetic field and like let's say this is the loop. So this loop we assume, and this is an assumed loop, not an actual loop, and this loop is called Amperian loop, okay? And dl is like the tangential length of small length along the loop, and it is B vector. It is magnetic field at this point where dl is situated. So I'll say B dot dl and line integral of that. So B dot dl and integration of this dot only indicates that it is around the complete loop, okay? So integration of B dot dl is mu naught times the sum of all the currents, algebraic sum of all the currents passing through this Amperian loop. So once we will do some applications of it, we will understand it in a better manner. So there are some important points regarding Ampere's law. So first point is, in order to apply Ampere's law, all the currents has to be steady. If currents are continuously changing, then it cannot be applied. Second is, only currents crossing the area inside the Amperian loop, okay, they need to be taken into the account. The current, if they are passing through the area which is not part of the Amperian loop, out of the Amperian loop, if current is passing, then they are not taken into the account. And last is summation of all the currents. Now summation of all the currents has to be algebraic sum. What does that mean? If currents are going out of the surface, they are taken as positive, and currents which are going into the surface, they are taken as negative. And if I amount of current is, let's say this is my Amperian loop, and if I amount of current is going like this, and at the same time I amount of current is going or enter into it, okay, then I will say the sum of all the currents is 0, because this is positive I plus negative I, which is 0. So the sum of all the currents has to be algebraic sum. So we are going to discuss the applications, and first application is magnetic field due to infinite long cylinder. Okay, so we have a cylindrical shell, and this cylindrical shell is having inner radius as A, outer radius as B, and the current is passing uniformly through its area of cross section, which is this, and I amount of current is passing through it. First is, we are going to discuss case 1. Case 1 is at a distance which is greater than B, means even greater than the outer radius, right? So for that, I am simply saying that let us assume an Amperian loop like this. So this is my Amperian loop, this is my R. So if I have to get a magnetic field at a distance R, then I will assume an Amperian loop which is circular, and this circle is having a center on the axis of the cylindrical shell. So I'll be saying that over here, how do we write it? We will say that as per the Amperian loop law or Ampere's law, we will say integration of B dot dl is mu naught into sum of all the currents. First, what is this? So this is simply, see, this is a cylindrical, infinitely long, right? So if the magnetic field over here is B, and this will behave as a like wire, so if current is going that way, then field will be into the plane, out of the plane. So we know that field is going to be tangential to this Amperian loop like this. So let's say B is produced, and due to symmetry we can also say that since at R distance only we are talking about, the field has to be constant in value, direction is tangential. So when I do integration of B dot dl, it will be B is constant, and dl is simply this length, and so I'm just writing dl, and then angle between them is cos of, see, the dl is along the tangent, B is also along the tangent, so cos 0, and integration of this, B is constant, it will come out, cos 0 is 1, so it will be simply integration of this length. So it is, we can say integration of B dot dl comes to be B into 2 pi R. That's the first thing. Second is, this is equal to sum of all the currents, mu naught times sum of all the currents. How much is that? So mu naught is mu naught only, and how much current is passing through this Ampere loop, I'll say the entire current I is passing, right? If I amount of current is passing through this cross section, then entire I is going in one direction. So sum of all the currents is simply I. And just equate these two and solve them for B. So I'll be saying that B is nothing but mu naught I by 2 pi R. And that's the magnetic field at a distance R, which is even bigger than the outer radius. The case number 2. This is mu naught I by 2 pi B. It should be 2 pi R. Okay, this is wrong. Now at a distance R we are checking, okay, not at the B. If we are saying checking at R is equal to B, then you can put R is equal to B over here because it is valid for R greater equal to B. Now second case is, what if our R, the distance from the axis, is lying between A to B? For this, let's have a look at this. So this is the cross section. Now the inner radius is basically, this is the inner radius, that is A. The outer radius is B. And now the current is passing through this cross section. So what I am going to do is, I am going to take a Amperian surface or Amperian loop again. So Amperian loop is having R radius. R is somewhere between A to B, right? So the red one is Amperian loop. Now I will simply write that what is integration of B dot dl. Again, due to symmetry, here we can say if current is coming, let's say current is coming out of the plane. So we'll be saying that B will be tangential, right? So it will be tangential. So B dot dl is simply again magnetic field, magnitude of magnetic field in that is along the tangent. So it is just 2 pi R because cos 0 will be again 1. So into 2 pi R, and R is basically 2 pi R is this length. So it is B dot dl. What about sum of all the currents? So for that I need to get the current which is passing through this. Now current is coming through entire cross section. I will be saying only this cross section. Whatever amount of current is coming through this cross section is the current which is passing through Amperian loop. The current which is passing through here, this region, will not be counted as the part of sum of all the currents. So I am simply finding first sum of all the currents. So sum of all the currents is this total current, which is nothing but current density into this area. This area is how much? Pi R square minus pi A square. The outer minus inner, right? So current density is what? Current per unit area into, so current per unit area into required area. So we got this. And here what is J? Current per unit area. So we can find that we'll say total current is I divided by total area. Total area is how much? Pi B square, the outer, minus pi A square, the inner. And then put pi R square minus pi A square. Now pi can get cancelled out, right? And we can put this I. Let's just put integration of this is equal to mu naught into sum of I. You can cancel, you can take I out here and then cancel it. So you'll get this expression. And now I am simply saying applying Amperian loop law. So it is B into 2 pi R, that's B dot dl, is equal to mu naught into current. So mu naught into sum of all the currents is I into R square minus A square divide by B square minus A square. And now to get B, this 2 pi R can simply go over here. So I'll get B is equal to mu naught I R square minus A square upon 2 pi R B square minus A square. So that's the magnetic field at a distance R, which is somewhere between inner radius and outer radius A and B respectively. So this is the formula which we just derived. And now next case. So next case is, what if R is less than even A? If R is less than even A, again do the same thing. Go with the, make a Amperian surface at R, and this is my R. But the thing is, no current is passing through it. So even though integral of B dot dl is going to be, let's say B is the magnetic field, we don't know how much is that, into 2 pi R. 2 pi R is this length of the Amperian loop. But the mu naught into sum of all the currents, the mu naught is mu naught, but no current is passing, so sum of all the current is 0. Hence this thing is 0. They simply say B into 2 pi R is 0. Now 2 pi R is a non-zero quantity, so that gives us that B must be 0. So here we'll say that inside the shell, the field is 0. In the middle, the field is, we just derived the formula mu naught I r square minus a square upon 2 pi r b square minus a square, and outside the field it is mu naught I by 2 pi r. R is the distance which is greater than b. So this is the last case and b comes to be 0. So those are 3 positions where we can get the magnetic field using Ampere's law. Now this is a question. The question says, infinitely long hollow conducting cylinder. Okay, this is a hollow conducting cylinder of inner radius r by 2 and outer radius r carries a uniform current. Okay, it carries a uniform current, and along its length the magnitude of magnetic field, okay, magnitude of magnetic field vector b as a function of the radius r or function of the radial distance r from the axis is best represented by which graph? So we know that here it is, my a is r by 2, the inner radius, the outer radius is r. Just think again, for r less than a, or to be precise r by 2, r less than r by 2, what will happen? The magnetic field comes to be 0. For r which is greater than b, that is greater than capital R, the magnetic field comes to be mu naught I by 2 pi r, right? So here it is 0 and here it is inversely proportional to r. So just check the graph. This graph is wrong because 0 to r, right? From the axis 0 to r by 2, it is linearly varying, which should be 0. So this graph is wrong. This we are keeping as of now. This also we are keeping because 0, and this also we are keeping. Now from greater than b means greater than r, it is inversely proportional to r. So that it meets with the criteria. This also meets, like it is inversely proportional. So graphs, this also meets. Now in the middle, the basically for r which is lesser than capital R and greater than capital R by 2. So we'll be saying that b is nothing but mu naught I r square minus r square by 4, that is r by 2 whole square, divided by 2 pi r and then capital R square minus capital R square by 4. And if you see that this is not a constant, because like as you can see here we have r square and here we have upon r. So if you just like forget about these constant mu naught I, 2 pi and this thing, so you are left with, it is basically proportional to r square upon r minus r raised to 4 by 4r. So it's proportional to that, which is a non-linear. So linear is cancelled, so this option is cancelled. This is again linear, so this option is also cancelled. Only option is this, which is basically starting from 0 at r by 2. If you put r by 2 over here, then this is r by 2 square minus r by 2 square, so you'll get 0. So 0 to a maximum, and then this meets with all the criteria. So correct option should be D. That's the answer for this question. Now this is the second application of Ampere's law, and this is magnetic field due to a toroid. So we are going to find first magnetic field due to a toroid. First we need to understand what toroid is. So toroid is a structure. Last time we discussed the solenoid. So solenoid is a structure like a spring, a spiral helix. And if you take a solenoid and then bend it and make a circle, okay, so we get a toroid. So toroid is a structure which is like a closed solenoid. So toroid is a structure formed by joining solenoid end to end. The magnetic field at a point P at a distance r from the center is given by first case. Case is, again there are 3 situations, 3 positions which we can discuss. So toroid has an inner radius, an outer radius, and we can say 3 positions are even at a point which is even away from the B, okay, from the center, or between somewhere between A and B, or even or somewhere where less than A. Okay, so R is less than A, R is between B and A and B, and R is greater than B. These are the 3 cases which we are going to discuss. First case is, what if R is greater than B? So for this situation, I am saying draw Amperean loop like this. Now if you see, this is basically a 3D picture. So current is, let's say current is coming, so current is going in, then coming out, going in, coming out. So when current is going in over here, it is coming out again from here. So current is going in over here and coming out. Now these two will cancel each out. Then when it is again going here, it is coming from here. So these two will again cancel out. The sum of all the currents I am talking about. So here also it is going in, coming out. So whenever the current is going in, it is also coming out, right? From within the Ampere loop only. So we will say in such case, what happens is sum of all the currents, that becomes 0. So we'll again write that integration of B dot dl, that is B into 2 pi r, that comes to be mu naught into sum of all the currents, which is 0, and it is this due to which the B comes to be 0. So we can say magnetic field at a distance which is even greater than B, here in this entire region, there is no magnetic field. So we can say that B dot dl we have already discussed, right? That this is Ampere's law. Then B dot dl comes to be B into 2 pi r, while the mu naught I, sum of all the currents, is 0, and hence we get the magnetic field as 0 in a region, in this region or the outer region we are talking about. Now next case is case 2, somewhere between A and B. So R is somewhere this dotted as shown in the figure. Now for this, again let's shift to the board. This is my solenoid, toroid, sorry, this is my toroid, and I am just saying let us talk about at a distance R, which is somewhere between A and B. A is inner radius, B is outer radius of the toroid. So now first thing is that here in what direction magnetic field will be. For that, all the curve loops, they are going in here and coming out from the here. So I am saying it's like this. The current is coming out from here and going in like this. And part of the loop is below the, and like that's rotating continuously, right? So I'll be saying that since current is like this, so just do this and you will say that it is along the axis. So at this point, the magnitude of magnetic field is in this direction. This is the direction. Let's say the magnitude is nothing but it just B. B is the magnetic field which is tangential. So for entire loop, it is tangential, as you can see. Now I'm applying Ampere's loop law for this. So I'll be saying that what about integration of B dot dl? That's same as usual. So since it is tangential, so we say B into 2 pi r, right? What about mu naught into sum of all the currents? So I'll be saying it is mu naught. What about sum of all the currents? So sum of all the currents is nothing but, we'll say, see, these currents which are going out of the plane are out of our Ampere loop. Only this current is entering here and this is entering. Here again the current is entering. Here also it is entering. So we will say if I is the current carrying by the toroid, then I times the total number of turns. The capital N is total number of turns. This amount of this total number of turns, this amount of total current is entering it. So this is sum of all the currents. Current in each turn and total number of turns, right? Now I'll be just equating these two to get the magnetic field. So I'll be saying B into 2 pi r is nothing but mu naught capital N I, and just this 2 pi r goes there. So B is equal to mu naught capital N I by 2 pi r. Now if you see this, this is mu naught the capital N by 2 pi r and I. What is N by 2 pi r? Total number of turns divided by 2 pi r. 2 pi r is basically the length, right? Length of the toroid. If you just open it up, the length is 2 pi r. R is the average radius, the inner plus outer by 2. A plus B by 2. So this is nothing but number of turns, total number of turns divided by total length. This is nothing but number of turns per unit length. And hence we get mu naught Ni. So this is the expression for magnetic field inside the toroid. So we'll be saying that it comes to be mu naught I naught, and eventually the final expression which we get is the N into 2 pi r. They have said total number of turn is number of turn per unit length into length, okay? And the final expression is same as the field due to infinite long solenoid on its axis. So at the axis of a toroid or infinitely long solenoid, the field is same in magnitude, and that is mu naught Ni. But here it is along the axis, and there also it is along the axis. Their axis was linear and here axis is circular in shape. Now the last case, the case number 3, if we are talking about R which is less than A. So again, I will consider a Ampere loop over here. But the current is coming out from here and going in there, or coming out from here and going in there. But we don't have to deal with that. This is the area covered by Ampere loop. And no current is entering or leaving that area. So again, same thing we can write. This is my Ampere's law. So mu naught into integration of B dot dl is B into 2 pi R only. But at the same time, mu naught mu naught into sum of all the currents is 0. Because no current is entering or leaving that Ampere loop. And eventually we get the magnetic field is 0. Again, inside in this region it is 0. In outer region here it is 0. Here it is 0. And inside the toroid, it is same as the solenoid, infinitely long solenoid, that is mu naught Ni, where N is the number of turns per unit length. Now we have a question. This question says, if the current density in a linear conductor of radius A, okay, so in a linear conductor of radius A is varies with R according to relationship, this is current density, J is equal to KR square, where K is a constant and R is the distance of a point from the axis of the conductor. Find the magnitude, find the magnetic field induction at a point at a distance R from the axis when R is even greater than A. A is the radius, outer radius, and inner radius is 0 because we are talking about a conductor. Assume relative permeability of the medium surrounding the conductor be unity. So basically it is free space only. Now let us say this is my piece of conductor. They are saying that here the radius is A. So what I am going to do is I am going at R distance and then I am taking a width of dr. This is my dr. So I am saying that if I have to get the magnetic field, okay, so magnetic field, then I have to at a distance which is even greater than A. So I am simply assuming my Ampere's loop. Let's just make the Ampere loop. So this is my Ampere loop. So this is my Ampere loop, and here for this Ampere loop I have to find the magnetic field, like magnetic field at this point. So I'll be saying that magnetic field, this is just the cross section of the conductor. So I have to get the magnetic field at this point. I am again applying my Ampere's loop law. I'll say integration of B dot dl is nothing but mu naught into I. I is the total current or sum of all the currents we should write. Then I'll say what is this? This is B into 2 pi R. What is R? Not this R. Let's just take that as R2. So this distance I am going to talk about. So this is, I am taking it as R2. So B into 2 pi R2 because I have to get magnetic field at this point. And is equal to mu naught into sum of all the currents. Now sum of all the currents is what? The total current which is coming out of this cross section. So to get the total current, here our J, the current density was a variable quantity. So to get the total current, you have to separately integrate. Just to get this total current, I am integrating. For that, what I am doing is, I am going at R distance, I am taking a width dr, and then I am saying how much is the current in that dr width. Current in this region. So current in this strip, which I have just marked, this is nothing but current density. I'll say current in this strip is nothing but current density, which is J, into area. Current density is current per unit area. So current density into area. How much is the area of this strip? So the length is 2 pi r. This strip can be long. So 2 pi r and width is dr. So 2 pi r dr. And here I'll integrate from dr. So change is happening in R. So I'm going to integrate from R is varying from 0 to A. So I'll get total current and eventually just integrate it. So I'll be saying that what was J? J was KR square into 2 pi R dr integration of that from 0 to a, r is changing from 0 to a, and eventually what are we getting? We are getting k constant, 2 pi a constant, and this is r cube. Integration of that is r raised to 4 by 4, and limit is 0 to a. So we will get 2 pi, you can 2 pi k a raised to 4 by 4. You can just cancel this out. This is 2. So this is our sum of all the currents. Now put it in this expression. So we'll be saying it is pi k a raised to power 4 by 2. That's the sum of all the currents. Now just solve it for B and we will get our answer. So B comes to be, this pi will be cancelled out by this pi, and then I can say that it is mu naught k a raised to 4 by this 2, and this 2 will be 4 and times r2. So at a distance which is basically greater than a, this is the expression for magnetic field. At a distance r2 is even greater than a, this is the amount of or net magnetic field. So next is, this is the third application of Ampere's law. Here we are going to derive an expression for magnetic field due to a current carrying conductor using Ampere's loop law. Now this is a current carrying conductor. So this is a current carrying current in this direction. First is the direction of magnetic field. So direction of magnetic field is given by right hand grip rule. So you just grip the wire, and if you see at this particular point, the direction of magnetic field is into the plane of the paper. If you see that here at this point it is towards right, at this point it is towards left, right, and at this point it is out of the plane of the paper, and here it is into the plane of the paper. So this is the direction of magnetic field due to a current carrying conductor. Now let us discuss what is the magnitude of that magnetic field. So first is that we are going to discuss that r is less than r for a distance which is less than the radius of the conductor itself. So here I have to get the magnetic field. This is just a cross section. When you have a look at the wire from the top, okay, so you see something like this, current is coming out of it, and here we are defining that current is nothing but current density into pi r square, that is current density into area. Current density is nothing but current per unit area. Now at r distance I need to get the magnitude of magnetic field. So what I will do is I will just draw this Amperian loop at a distance r, and now I will simply write the Ampere's loop law. So if I write the Ampere's law at r distance for this particular point, what does it give me? That integral of B dot dl is mu naught into I naught, or sum of all the currents. Now what is B dot dl? B dot dl is simply B into 2 pi RC. Magnitude of magnetic field is a constant quantity at r distance by the symmetry, right? So we will be saying magnetic field is B, and integral of dl, the total dl add up to 2 pi r, right? Now mu naught is mu naught, and now I naught is the total current passing through this region, and now that region is how much? So current which is passing throughout the Ampere's loop law is nothing but current density J into area, that is current per unit area into the required area. Now I know that J is nothing but I by pi r square. So if I put my J as I by pi capital R square, and I cancel this out, and eventually this R is cancelled, then I can get an expression for B that comes to be, this 2 pi will just go in the denominator, mu naught I R upon this 2 pi capital R square. So that's an expression for magnetic field, and here we can see that B is directly proportional to R. More away you go, increases the magnetic field in magnitude. So we can make this expression, it is mu naught J R by 2 or mu naught I R by 2 pi R square. It is directly proportional to small r. Here mu naught I and 2 pi R square, all the things are constant quantities. Now next is the second situation where we are going to talk about a distance which is bigger than this capital R right, r dash, or I am writing that here we are going to talk about a distance which is greater or equal to r. So just at the surface of the conductor or for a point which is outside it. Now Ampere's law at r dash, what does it gives to us? So we are saying again B dot dl is equal to mu naught into sum of all the currents. Now same thing, B dot dl is just magnitude of magnetic field into 2 pi r. And what about mu naught into I naught? Mu naught is mu naught and I naught is the total current passing through Amperian loop. So this time Amperian loop is big enough so that it is covering the entire conductor. Entire conductor is being covered, or within that, passing within that Amperian loop. So we'll say total current I is passing through it. So current is nothing but J into pi r square. This is total I also. So if you just write total I over here, then you will get mu naught into total current divided by 2 pi r dash. So this is then expression for magnetic field for a conductor just outside it, right? In terms of J you can write that, or in terms of current you can write mu naught I by 2 pi r dash at a distance r dash. Now this is same as the current due to a wire, right? So this is a thicker conductor which will behave as a wire for a point which is lying at a distance bigger than its radius itself. If we are talking about the surface, then for surface what needs to be done? In this expression is valid for r dash which is greater or equal to r. Just insert r dash is equal to r. So once you put r over here, you get this expression. So at the surface, magnetic field is given by this formula or this expression. Now there is a question. This question says that a coaxial cable consists of a thin inner conductor fixed along the axis of a hollow outer conductor. So there is inner conductor and outer conductor. Now the two of the conductor carry the same amount of current, same equal currents in opposite directions. So one conductor is carrying current above and one is like carrying it in below direction. So direction is exactly opposite. Let B1 and B2 be the magnetic field in the region between the conductors and outside the conductors respectively. So if we make the diagram of a cross section, this is my inner conductor, this is my outer conductor. The inner conductor is carrying a current, let's say, into the plane of the paper. And the outer conductor is carrying a current out of the plane of the paper. The total amount of current in both of them is equal, but the direction if you see is just opposite. One is into the plane of the paper and one is out of the plane of the paper, and this is the cross section view. So they are saying at this particular point between the conductors, right, the magnetic field is B1. Let B1 and B2 be the magnetic field in the region between the conductors and outside the conductors here. So we will be saying that now they just want to check what is B1, what is B2, whether they are 0 or non-zero. We just need to check that only. So we will be saying that for B1, if I draw this Amperian loop, then through this Amperian loop, see, outer current is not contributing at all, but inner current, there is current which is going in the Amperian loop, and hence we will say that B1 is a non-zero quantity. So B1 is not going to be 0. But what about B2? If we are drawing this Amperian loop for B2, then we will be saying that whatever amount of current is going into the loop from the inner conductor, same amount of current is coming out. So total current, see, I current is going in the loop, I current is coming out of the loop. So from this bigger Amperian loop, no net current is passing. So if current is 0, then magnetic field will be also 0. So we'll just write B2 into 2 pi r is equal to mu naught into 0. Hence, we'll get B2 equals to 0. Now B1 is non-zero while B2 is a 0. So our C option would be the correct answer.